Students, welcome back to part 2 of lecture number 29. So, we will elaborate more on this concept of materials design at different length scale or materials at different length scale. Okay. So, let me start first example of this, okay, which is a very important discovery in the field of material science or rather engineering, what is known as a gas turbine engine. And these engines are used by the aircrafts or aero engines, it can be used even many other purposes. So, heart of the engine is basically this is nothing but blades. You can see the blades like that, which are arranged over the periphery of this rotor, and that is C1 which I have obtained from this website mdaturbine.com, and this is a very typical feature of any turbine engine. Now, once we know that they rotate at a very high RPM, I talked about it in some time back. So, what kind of materials you will use? From 1940s to 2020, you could see this paper from Wright and Gibson provides you recent developments. And initially, we always use superalloys. Superalloys are nothing but high, they contain many alloying elements that contain about 14 elements in the material, but mostly it will be nickel, cobalt, iron, aluminum, chromium, like that, but there are many other elements possible. And as we see here, initially we used to use wrought or deformed superalloys, then from 1960s onwards we are using cast superalloys, from almost 1970s we are using directionally solidified superalloys, 80s onwards we are using second generation single crystal superalloys, from 2000 onwards we are using third generation, now we are talking about fourth generation also. The generation means the chemistry as well as the processing conditions, but they are all single crystal superalloys. So, this means this kind of big blades are actually single crystals, and now we are talking about can you change the chemistry of the alloy, can you use from nickel based superalloys or nickel cobalt or something iron superalloys, less more moly silicon based boron alloys. Well, it is still under experimentation, that is why they have put a question marks, but so far so good, we are using only this third generation to fourth generation superalloys. That is what it is. So, now I will show you that many of aspects. These are the blades which you use, as you see here, this dimension is a different kind of blades we can use it. And these blades actually either can be equiax crystal structure or they can be directionally solidified. Equiax crystal structure means cast, only cast superalloys, or it can be directionally solidified, then you can also multi-grains, or it can be single crystal also. The best application requires use of single crystal superalloys. That is the key aspects of this dimension. And I like to say that these blades actually of a dimension of a meter. So, they can be as long as a meter, okay, if not 60 to 70 centimeters in some cases, but it can go up to 1 meter also. That is the dimensionality of these components. So, now let us look at down the scale. If I go down the scale, so because we material science engineering students, we need to know more about the microstructure. That is what we are talking about, how we can go down the dimensionality. So, first obviously, if you want to see something which our naked eyes cannot see, you have to use microscopes. So, one can use optical microscope or scanning electron microscope or transmission electron microscopes or even better techniques which to see the atoms. So, if I see that any blade will have three main structures. First is this is the main blade, a superalloy, then a N5 superalloy, which is again a nickel based superalloy. Then after that we put some kind of a bond coat, which is platinum aluminum type of alloys. You can see that this is the bond coat which is shown here, and the top coat is nothing but a directionally grown zirconium oxide, yttria stabilized zirconium oxide, about 7% yttrium oxide with zirconium oxides. That is basically thermal barrier coating, because as you know these blades will be withstanding high temperature, something like about 800 to 1000 degrees Celsius temperature. So, they should not get oxidized, they should not get affected. That is why you need to put a top layer of zirconium oxide, which has a very low thermal conductivity, and they are directionally grown, so that they can actually retain their insulating properties. But because of the thermal mismatch, thermal conductivity mismatch between the zirconium dioxide and the superalloy, there can be thermal stresses. That is why this underlying layer between these two are kept, that is platinum aluminide layer, and this can actually get oxidized and form aluminum oxide, thermally grown aluminum oxide, you can see on the top of this. So, it is a very complex structure, it has 4 different layers: zirconium dioxide, thermally grown aluminum dioxide, TgO is thermally grown aluminum oxide, then you have bond coat, and then you have a superalloy. That's what it is. And you look at the dimensions of this, they will be of the order of few microns, maybe some 10 to 15 microns, except the blade will be very, it will be quite thick. Now, if you want to see the microstructure in detailed manner, so this is the one which is the blade, we will talk about it more. Then this is one which is forming in the bond coat, and then you have a gamma aluminides, you can see here the gamma alumina, and you can also beta alumina, remember this, and then you have a zirconium dioxide layer. That is what happens, let us stop of that. So, these are these papers were from all these pictures are collected from these papers. Okay, I want to acknowledge the research done by them. Some of these papers are also, I am also co-authored, but some of them are not. So, now if I want to look at details of this blade which you are talking about it couple of minutes back, it has a typical gamma pine microstructure. Now, it requires to make you understand what is gamma pine, but it looks like this kind of checkerboard structure. For you, if you are not used to this kind of microstructure, this is like a checkerboard kind of microstructure, you can clearly see. So, and one phase is gamma, other phase is gamma prime. What is the difference between that? Gamma is a disorder structure, disorder FCC structure, and gamma prime is nothing but a order FCC structure. So, that is what is top one is gamma prime and bottom one is gamma. Okay, you can see that actually. This is the gamma and this is gamma prime. So, this has the phase center atoms which I have drawn for diamond cubic structure, basically has one type and corner atoms other type. So, now if you want to look at this structure, this is diamond, if you look at the dimension 500 nanometers, that is nothing but a 0.5 micron. And if you want to look at the structure in under scan electron microscope, they will also look like a checkerboard, but look at the dimensions and the features, they are different. So, if you want to magnify this structure, this will look like this, you can see big blobs like a checkerboard structures. So, majority are the gamma prime, these big blobs, and these black areas which are marked here, they are gamma. And between gamma and gamma prime, there is a very nice microstructural coherency, and that is why this gamma will never grow, gamma prime will never grow, they will remain in the same size, and that is why this is a wonderful material. And in order to stop the growth of gamma prime at high temperature, we have to add so many elements. So, now one can actually go down even further, look at atomic level structure. What is that? These are not atomic level, but these are TM, transmission electron microscopic images. If you go down the structure, you can see that these are the different types of atom present between gamma and gamma prime. I am only showing you cobalt and nickel. You can clearly see in gamma prime, cobalt and nickel, cobalt is less, nickel is more compared to gamma. So, gamma is basically, nickel is getting partition between gamma prime and gamma. Gamma prime will contain more nickel, it has a Ni3Al structure, so it must contain more nickel than the gamma. Gamma is a random structure, FCC structure, but the other hand cobalt is more in gamma, less in gamma prime. One can do all kinds of analysis, I am not showing everything. Just to show you that we can do atomic level structural analysis from this component to the atomic level. That is the key aspects of key reasons I have given this example. This example, this is true example of microstructures at different length scales, not only for the blade which you have seen, but also to the atomic level. So, once you have this kind of things, that is what we call a materials design at different length scale. If you want to design the material properly, you should do design from atomic level to the component level, if you want to be successful to build a component. That is what it is, that is the key aspects of that. And how do you do this? That is what we are going to learn in this 3 to 4 lectures. So, now let us even discuss about one of the best discoveries of the last century, that is the aeroplane, right. So, it normally takes about 20 years to develop a new material. I mean to say, starting from scratch to the application, it takes about 20 years. And you can clearly see from 1906, that is why the Wright brothers discovered the plane. The picture shown here taken from Wikipedia. and this is the plane they made, Wilbur and Oliver and these two Bright brothers actually. And then from there, this is a picture from 1990s. You can see how the changes happen. So, what is the body of the plane made up of? It is basically aluminum copper alloy. It has to be light, it has to be strong, and it should be able to withstand the air gust. When they moves from ground to the sky, there are a lot of air gust, right? It has to withstand that, especially the wings and the fuselage part of the or the tail of the plane, right? That is what is very important. And the probably air gust will be the maximum at the front when where the engines, where these pilots are sitting, right. So, what kind of materials we use? We can use all kinds of materials, you can think about it. Started with aluminum copper, which is the classic duralumin, okay. Aluminum copper is a duralumin actually. I hope you understand the meaning of duralumin, durable aluminum, that is what it is called, duralumin. And then one can add about 0.05% tin, or you can add 0.3% magnesium and silicon, silver, lithium, everything depending on, and you can actually make it stronger and stronger. By designing that, by doing the chemistry, what you are doing? We are making the material more stronger, better, and that is the idea. So, and this you see, this is how this process, this all is processed by aging treatments at certain temperature, this temperature is 200 degrees Celsius temperature. So, for the classical aluminum copper alloy which is used in these planes, the strength can be of the order of maximum hardness can be 100. But if you look at aluminum, copper with some amount of magnesium, silver and lithium, it can have a double the strength. That is what it is, more than that. So, we can actually then reduce the thickness. So, you reduce the weight of the plane. This is the idea. How it is possible and why it is done? Because with global competitiveness and also societal aspects that requires us to go for material discovery which will be faster and cheaper. So, now with the advent of this machine learning, all these things, we have a new subject called ICME, okay, integrated computational materials engineering, not only. So, that means this is nothing but a how to add, how to, this is a promising computational approach with experiments, with some kind of a experiment, that is what it is, and this one will be widely used in future. This is called integrated, I stands for integrated computational, C stands for computational, M stands for materials, and E stands for engineering. That is ICME. It is a new branch, new things come, and which will change the global perspectives of that. So, new approach is very simple. We start with atoms, develop quantum mechanical based models, and that is what you can understand atomic level physics, or rather even subatomic level physics. That is what we are talking about when you talk about carbon atoms. And from there, we can take the clue data and develop thermodynamic models, which can allow us to calculate phase diagrams. Because most of the applications we do in real world is basically alloys, and alloys means there has to be typical phase diagram based analysis. So, from quantum mechanics you have to go to calculation of phase diagrams, and not only that, once you calculate phase diagram, we also need to study what will happen in terms of kinetics. If you want to manufacture something, how kinetics is going to change. If you apply a thermal gradient, if you apply temperature, if you apply some kind of field, how is going to change. So, this the divide separating material science and materials engineering is very clear now, because here we are going to make a component, we want to make some objects, we want to make some components, and that is why we need to connect the material science aspects, which will be generating a lot of data using quantum mechanics or other kinds of theories, to manufacturing, and that is only possible when you combine these two domains together. And as you know, many of you know that American Society of Metals have produced various kinds of metal handbooks, and these metal handbooks will give you a lot of different kinds of data, and these data are very useful for various kinds of purposes. So, one of the examples of to give you an idea is cylinder box. This is a car engine, okay. This is a car engine, it is a cast, and that is why it is taken from Ford Research and Advanced Engineering. I would like to thank you them. And so this shows, this is the car engine block, which is a single cast engine. You can see how complicated shapes are that. So, but it contains, it is basically made of aluminum silicon alloy, mostly hypoeutectic alloys. And what will have? It will have aluminum, we will show some microstructure now, and with the silicon needles. It can also have a little bit of copper, okay. Then you can have precipitates like what you have seen in case of planes. So now you can actually go from casting to the microstructure to the atomic level. And this is a typical phase diagram of aluminum silicon. As you can clearly see, it is eutectic at something about 577 Kelvin. So we used near about 20 atom% of silicon, sorry 20 atom% of silicon, or something like about 11% of weight % of silicon for the alloy. And these engines are widely used for all kinds of cars, because they are lightweight, they have very high thermal conductivity, and they have structural stability. So the virtual modeling has to be done from manufacturing the car engines to the atomic level. So traditional product development is how it is done. Initially started with some geometry, like the car engine block has certain kind of geometry. Then you can actually make some kind of design of the geometry. After that you can actually make these components. So what you do is basically, before you make the components, what you do? You basically have a database of material properties, which can be used to predict the service life of the components. You can also have some input from your actual experimentation like load, and whether the component is durable or not. And then after it is done, then you can make a model casting. That is what your experimentation is. So as you clearly see, well, that is not experimentation, okay. So these areas basically, this is a database. So this prediction service life can be done by Abacus, but model casting can be done by ProCast software or a MagmaCast software, right, MagmaSoft. These softwares allow you to make the casting on the computer, and then you can actually check whether the castability is there or not. Since you are using a new material, castability is big issue, right, that you have to check. So then finally you can build the casting, test it. If it works fine, if it does not work, go to rebuild, retest, and you can do many times this, right. That is the traditional product development cycle. That is why it takes 20 to 25 years if you start the new material. So this is going to take time, more time than what you expect. So what you do is, instead of that, you remove this part, remove this. Modern design aspects does not want to do experimentation, rebuild, retest many times. What you can do, you can take from the feedback from this ProCast or MagmaSoft softwares and feedback and initial geometry, and do this cyclic things many times, so that you get an optimum design ready for the model casting, and which is very less likely to fail during the actual casting making. That is why you can reduce this cycle time. So therefore, for aluminum cast structures, what you do? You have a chemistry, that is the compositions, that will allow you to generate thermodynamical or kinetic databases, that the kinetic features like phase diagram or diffusions. So then you can do a casting, virtual casting by the way. So once you do a virtual casting, you can test even microporosity, you can even test the microstructure like precipitates, eutectic phases, aluminum silicon copper alloys, both are eutectic and precipitate phases. And then you can actually also do some kind of a heat treatments, and heat treatments can be solution treatment or edging if it is aluminum copper silicon alloys, that can allow you to study the precipitations. So with this process you can generate both the thermodynamic and kinetic aspects from the chemistry, as well as you can study these properties, the microstructures. Once you have understood the microstructure, then you can do properties of elements like yield strain, thermal growth, high cycle fatigue, low cycle fatigue. Remember, in a car engine, fatigue is very important, because every time you are burning the engine, basically the piston moves and down, so there are a lot of fatigue involved. It can be either low cycle or high cycle depending upon how you are utilizing the car, right. If you are going for a long drive, it will be high cycle. If you are going for a short drive, it will be low cycle fatigue. So these are the aspects. Then strength is very important also. Secondly, the microstructural features can grow during application of temperature, that is called thermal growth. So these are the basically aspects one has to understand. So, material engineering is all about finding the best thing. We need to find a means to conduct these quantitative trade-offs, all these quantitative things which you are doing. You do not need to do any experimentations, you can do design aspects using a different length scale, using these different kinds of softwares. So, to give you more better perspectives of the length scale problem, so car engine is 1 meter long, and if you want to do a simple optical metallography, it will be 1 to 10 millimeters. So, you go down from 1 millimeter, that is about 1000 millimeters to about 10 millimeters. So, you can see the grains, you can see the grains here, you can see porosities also, you can see the black porosity. You can also measure properties like high cycle fatigue and ductility also. So, now you can also look at under scanning electron microscope, there you can see about 10 to 500 microns, which is again under 3 order of magnitudes. So, this is 1 meter to this is like a 3 order of magnitude less, from there to here is another 3 order of magnitude less, and then here you can find eutectic phases, dendrites, microporosities, or even intermetallic phases. Properties which will be controlled by them are basically either yield strength, tensile strength, high cycle fatigue, low cycle fatigue, thermal growth and ductility. So, finally, you can go down even further to nanometric, that is another 10 to the minus 3 scale down. You can see the precipitates, you can clearly see the precipitates here, and the precipitates will control yield strength, tensile strength, fatigue properties, ductility, everything. Finally, you can go down even to the scale, go down to 0.1 nanometers, which is atomic structures. There you can find out the crystal structure, interface structures. You can see the interface between the precipitate and the matrix, right? And this will control thermal growth, how the precipitates can grow or not, yield strength. Obviously, if the precipitates go, yield strength will drop, right? So, this is in a nutshell how the length scale are very important to be understood in a materials design. We have to design for starting from the millimeter level components to the Armstrong level things. That is why I talk about it. Armstrong level you can see the atoms. So, this is the key aspects what we are going to discuss in this. So, key metallurgical processes which occur at many length scales like diffusion, thermodynamics and other things, all can be influenced by the history of manufacturing, how you make a component. So, to give you better perspectives, like in this case of aluminum silicon copper alloy, you can have silicon aluminum eutectic here, you can see here aluminum dendrites here, and then you have precipitates. So, precipitates can be seen easily, these are taken from our own literature, and you can also have porosities like this, the black color things, these are porosities, and you can also have some intermetallics, you can see here Al15, Fe3Si. So, these are all there built in the microstructure, they are going to affect the properties of your component. So, let me just tell you that. So, we need to basically integrate all the data science with the approach we are talking about it, materials design at different length scale, that is what is done in ICME. So, what you do is we have to do some experiments to find out data, but then data can also be used can be also generated by, or rather can be used for generating phase diagrams. We can do first principle calculations to feed the data, we can do statistical thermodynamics, which that can allow us to generate phase diagrams, and we can also use this to for better predictability and prove it experimentally whether correct or not. So, that will allow us to find thermodynamic properties, kinetic properties, mechanical properties, also interfacial energies properties like lattice parameters, everything. So, I have listed all these different kind of properties which can be measured. So, virtually speaking, actually speaking, it is integration of the data science with this materials engineering at the all length scale has to be done, then only we can do a better job in terms of modeling. So, let me stop here. I think we have discussed all these aspects in a detailed manner, and we will talk about more of these aspects in the next class when we start with one of these length scale like phase diagrams and slowly go down from phase diagrams to molecular dynamics or density functional theories, or even go up in phase field modeling or something, which we will do that. So, this is the key aspects or key things which we will be learning, and each of these techniques we are going to generate a lot of data. Handling data and modeling using data is going to be very important when you talk about design at different length scales. That is the main key aspects of what we are going to talk about it more on this. So, this is just the introduction, another introduction for the subjects, because many of you may not be from the field of microstructure or materials manufacturing. So, you need to know these aspects if you want to design at different length scales. So, let me thank you. We will come back to the lecture number 30 in the next and discuss more about this.